Well,
Great. And then here is the clicker.
Okay.
So everything should work, but we're right here.
thank you. Okay, good morning. Thank you. I want first to thank the organizer for giving me the opportunity to make a review on the solar neighborhood studies. And I will first start with the motivation. Why do we want to have a nearby sample? It's because it serves as an anchor. It contains all objects that can be seen and studied with the best precise data. It provides a calibration point on all type of stars. It provides also a complete and homogeneous sample, which is mandatory to eliminate any observation bias. And it brings fundamental constraints that can be used to understand more globally stellar physics and the Milky Way. However, magnitude-limited samples are biased against intrinsically faint objects. We know that low mass stars are dominant in the Milky Way, but even the brightest one is invisible to the naked eye. So that's why that long-term efforts have been made to get volume-limited catalogs. And the first individual measurements of stellar parallax in the 19th century have been followed by systematic programs. And I put here a list of such programs going to a few hundred stars with trigonometric parallaxes to several thousand of stars during the last 2 centuries. And here I put a picture of Louis Jenkins, who listed the list of all stars known within 10 parsec with their companions and all the knowledge at that time. In 1937, there were 127 stars. And I will show that the work is still going on. Then the 20th century was marked by the first astrometric space mission, Hipparcos, going outside of the Earth's atmospheres, allowed to have the measurement for much smaller angles and the precision, which is about 100 times better than what we can get from the ground base. Sorry, the ground. And so Hipparcos listed parallaxes for 120,000 stars. And you can see here the very clean absolute magnitude color diagram obtained from Hipparcos, which is mainly focused on stars that are more bright and more massive than the sun, or brighter than the sun. And then this was followed by the Gaia mission, which is still ongoing for a few months. And once it's an increase of 100 times in precision in the measurement of angles, and it goes to a fainter magnitude, and it provides parallaxes for 1.5 billion stars, which allows to fill out all the diagram down to the stellar-substellar limit, which is somewhere here. And you see also the cooling sequence of white dwarf, which has a lot of objects. I also want to talk a bit briefly about the efforts made by the research consortium on nearby stars, which in parallel of all this. Sorry. Okay, so this consortium focused on the detection and characterization of nearby stars and systems for several decades. And a lot of results have been published in a series of papers. I counted 51 papers from the last 30 years. And I will not talk much about that, but just encourage you to come at the Solar Neighborhood Splinter this afternoon, where Todd Henry will give the last news from the consortium efforts. Now, if we go towards the brown dwarf regime, the census have been filled out this last year with infrared observations, so the WISE mission, also the Spitzer follow-up parallaxes, and many other ground-based efforts. And this allowed to get parallaxes down to the early Y brown dwarf. And there are two important works that have been made, one by Best et al., who published 360, let's say, all L0 to T8 brown dwarf within 25 parsec, and Kirkpatrick et al. all LT and Y dwarf within 20 parsec. And these start to be quite important samples. And for instance, here I plot this is a color absolute magnitude diagram of the best étale sample, and you show the L dwarf here, and then the L to T dwarf, which make this blue shift in the diagram. And you can see an evidence of the gap here, which occurs at the LT transition and imply a rapid atmospheric evolution as a brown dwarf cool down. And this is the first time it is shown because we have start to have large statistics. Today's state-of-the-art stellar catalog covers 3 distant ranges. So with Gaia, we are able to have parallaxes for all stars within 100 parsec. There is also effort at the intermediate volume, 25 parsec, for instance, which have stars, but also fill out the census with brown dwarf. And the very nearby parsec, 10 parsec, where you can also have information on exoplanets. And just in one year, last year, there's 3 papers I put here were cited more than 100 times in many studies, and showing that this catalogs cover a large potential of scientific exploitation in many fields of astronomical research. I will go briefly through these different catalogs. So the Gaia catalog of nearby stars was made only with Gaia data, and it's a census of all stars within 100 parsec, and it was able to double the number of stars with a trigonometric parallax at 25 parsec and multiply by 10 at 100 parsec. And I want to stress out that you cannot just download the catalog and make a simple parallax cut, because you will get many spurious data, which are shown here. In particular, in crowded region, you have twice more rejected objects with bad astrometric solutions than real objects kept in the catalogs. So it means that the work needs to make some classification, more random forest classification. So it's a very contains many stars, but brighter stars are missing because it's based only on Gaia, so you have saturation problem. It has an incomplete white dwarf and brown dwarf samples and limited unresolved binary information. Going to the smaller volume, recently the Golovin et al. Published the 5th catalog of nearby stars, which has all stars within 25 parsec. And it has a complete white dwarf sample and goes to brown dwarfs down to the spectral type L8. Still 1/3 of brown dwarfs are missing at the later tape, and there is no unresolved binary information. In the same kind of volume, the Kirkpatrick et al. Recently this year published the full sky 25 parsec census, which contains all stars and brown dwarfs within 20 parsec. So this is more than 3,000 stars and objects, which is means long effort to check, and part of the list was vetted by a group of citizen scientists. And they did a huge work to decompose each multiple systems in its separate components, which was used to measure the initial mass function across the stellar to substellar regime. Still, it's incomplete for late brown dwarfs, late that starts around 15 parsec, and I'm sure that Devi will tell you everything you want to know about brown dwarfs on Friday. Then going to very small volume, we published the 10 parsec sample some years ago, which was first focused on objects observable by Gaia as a quality assurance for the Gaia catalog of nearby stars. And we complemented it to get a full census, including bright stars, close binaries, brown dwarf, and exoplanets. These are some statistics that we draw from this sample. 60% are M dwarf, with a peak around the partly to a fully convective transition in the main sequence. There is 4.4 more stars than brown dwarfs. They are dominated by late T's and Y dwarf, and a multiplicity frequency of 27%. And if you go to the Rincon's website, you can find this plot, which was made 25 years ago, and it helps to understand how the sample has evolved in 25 years ago. Sorry, in 25 years, oh, 15 years. So nothing much new regarding white dwarf and massive stars. But a lot of discovery has been made, M dwarf as companion in systems. Also, regarding brown dwarf, the discoveries of the new type white dwarf, but also late type T dwarf have been discovered. And the number of exoplanets is about 8 times than 15 years ago. So now some example of scientific use of this catalog. So I plotted the color absolute magnitude diagram of the different sample. Gray is 100 parsec superimposed with 10 parsec in color. This is the CNS 5 here in the Gaia band. And here you have the continuation on the substellar regime in the WISE band. And here you have also the full sequence in the infrared, near-infrared, mid-infrared band, 20 parsec. And the first obvious thing when you have this very nice diagram is to count the number of stars per magnitude and per unit volume, which gives you a space density or luminosity function if you correct for the volume. And this was done with 100 parsec and 25 parsec here in the visible Gaia band, and here for brown dwarf in the WISE band. And you see it's very clean. Error bars are often smaller than the size of the symbol. And you can see some features that you can believe are significant. And in particular, there is this dip here that we explain as being the stellar-substellar boundary in the fields, because brown dwarfs cool with age. They will depopulate the earlier spectral type to go to later one on the right of the diagram. And then we expect a minimum in the density at this boundary, which has been shown earlier, some time ago by us in simulations. And for the first time, it's observable, thanks to the high precision of these catalogs. Then once you have the luminosity function, you want to go to the mass function. And this is quite easy. No, it's not easy, but for stars, it's the mass estimation works quite well because there is a correlation between the luminosity and the mass on the main sequence. And it's not the case for brown dwarfs. We cool with time. So for a given spectral type, there is a degeneracy between mass and age. And this is shown in this evolutionary curves, cooling curves for stellar and substellar objects from the Sandy models. And you have the hydrogen burning limit here in black that separates the main sequence that attain a steady state and the brown dwarfs that cool down forever. And so you have this degeneracy at a given effective temperature where you can have a low mass young brown dwarf or higher mass older brown dwarf. Eventually, you can still get this kind of nice relation between mass and spectral type, but usually you really need a statistical approach to get information on the mass function. So you need to do some prediction of the luminosity function, assuming various forms of the mass function. Also, you can test a different birth rate function, and you can also test some low mass cutoff. And need a theoretical evolutionary model to get the age of the object. And this was done in these two studies where there is the model, the simulation are overplotted on the observations, and several the grid of simulation, assuming different parameters are used to find the best fit model. And I give here, for instance, one result from Rago et al., who were able to find the slope of the initial mass function, and they also conclude that the low mass cutoff for a star, brown dwarf formation, is lower than the 5 Jupiter mass. Another example of use is in this paper, which makes the chronology of our Milky Way and gives a really detailed view of the evolution of the Milky Way from a color magnitude diagram fitting of the 100 parsec sample. It has been complemented with line of sight velocities, and metallicity alpha abundance elements from the Gaia spectrometer. And they are able to trace the star formation history of the Milky Way. So if you have 14 gigayears ago here and today here, and you see all this starburst going on during the history of the Milky Way. And they did even better because they do the same thing, but as a function of metallicity. So they were able to trace the earlier star formation at low metallicity. And you can see here all the starburst in the more recent times, and they were able to get an accuracy better than 6% in the dating of stellar population. I will go quickly on this one, but if you have a radial velocity and proper motion, you have all the information to get the kinematics of the object, and even in the solar neighborhood, you see that this is a two-way diagram that is used to separate the different population. And in the solar neighborhood, you have a lot of visitors from the halo and eventually and the thick disk. And the kinematic plane is highly structured in the disk due to dynamical effect. And this is seen also in such a small volume as 100 parsec. And maybe Jennifer Winters will talk about that later today because she's talking of spectroscopic survey. So what next? Are we all done? So Henry et al. Asked this question some time ago. So you have here the known systems at this time. And assuming that we know everything at 5 parsec and the density is constant, you can extrapolate. And you see that you have at 10 parsec, you have 130 missing systems. So today, it seems that's okay, we are done. The job, but no, because a new system has been found in 5 parsec. So if you redo the raisonnement, you will find that today we are missing 90 systems. So it looks like a never-ending story, unless we question the assumption that the density is constant. Maybe the fluctuations that are shown here are real. And Scholz and Mintz showed that actually they can partly explain the apparent deficits. But still there are some work to do. So we expect to resolve multiple stars in systems with different techniques, spectroscopic, adaptive optics, and so on. And for instance, here I put a recent paper, follow-up astrometry from HST of Luhmann 16, who opens the door for the existence of a third body. Also, we may find faint white dwarf in unresolved systems. There are actually 2 candidates in the 10 parsec sample, and extremely cool objects hiding in the Milky Way plane, such as this one that has been found 2 years ago. Focus on exoplanets. First, Gaia, we expect from Gaia to find 10 to 20 new cold giant planets from the perturbation of the orbit of the host star by the planets. And if we believe Kepler results, we should have 2 to 3 small and close-by planets per M stars, which result in about 600 exoplanets in the 10 parsec sample. At the moment, we have 85. There have been 6 discoveries between 21 and 22, and 3 candidates, but nothing since then. So either we have reached a plateau, or we all should push forward on these topics. And I will let José Caballero answer this question this afternoon. And the future also may find brown dwarf and planetary mass objects thanks to the near-infrared sample, in particular the Euclid, which is providing a large homogeneous near-infrared sample that can be used to study the demographics of stellar population, but also we expect to find rare, extreme, and faint so close by types. Here I plot what we know, the number of objects as a function of a spectral type, object with spectroscopic spectral type. And probably we are missing objects in this faint part. And prediction has been made on what we expect to have. So in Euclid, we will have a volume which is 3,000 times larger than 2-mass survey and 300 times larger than Euclid. And Solano et al. Predicts that in the wide Euclid-wide survey, we should get 1 million L dwarfs, 0.5 million T dwarfs, and a handful of Y dwarf. And in the deep field, a few thousand T dwarfs. So probably some of them will fill the nearby samples. And these plots show the effective volume for detection of a mid-L type, L5 dwarf, since 2000. And it was about 10 to the 5 cubic parsec with Dennis SDSS and 2-mass, and has been multiplied by a factor 2 order of magnitude with Subaru Yuki's Vista Des, and about the same increase is expected with Euclid and complemented data, Rubin and Roman. And as an illustration on this very cool object, I will show you here a result obtained from the early really observation of Euclid. And this is, okay, thank you. And this, okay, this region of the sky have been observed. It's only 0.6 square degrees, so it's very small compared to the thousands of square degrees that Euclid is scanning. And in this field, here you have the magnitude color diagram with the stars in the field, and here you have some low mass object. You have the mass here and superimposed with the Atmo isochrones. And in this very small field, 6 new planetary mass candidates have been found. There is also no evidence for low mass cutoff below from Jupiter mass. And okay, this is Sigma Orionis and a young age, so it's not exactly a very nearby sample, but it illustrates what can be done with Euclid. And I will just finish with this video that has been made using a subsample of the Gaia catalog of nearby stars. It's 70,000 stars with radial velocity, so we have all the information with proper motion on the motion. We can compute the orbit and see how the small dot, which is a 100 parsec sample, will move with time. And actually, you see that in 5 million years, all the work we have done will have to be redone. So it's a bit, okay, pessimistic takeaway message. But it shows also that with the very precise data that we have today, we can have a better idea of what will be our solar neighborhood and what was our solar neighborhood before. You can maybe not see, but on the edge-on view, you see that there are some stars that are going quite far from the plane, which are actually visitors from the halo. Stars are also going very close to the galactic center, so there are a lot of different type stars, even in this very small solar neighborhood. And at the end, we will be all dispersed all around the galactic center. So, thank you very much.
So just take a deep breath for a second. I just want to remind everybody that we're asking for questions, not comments. And if I could just ask the speaker to come up, get ready before we start the questions up.
Thank you for a beautiful talk. With the excellent census of local stars, you get the mass potential of the galactic disk. And with proper motions, we get another estimate of the mass in the local region. So the question is there any evidence for dark matter? Locally.
I don't. I think there are some if publications trying to look at that in particular with Gaia, but I don't have any result on mind.
I will speak loudly. Tell us a little bit more about the local age distribution. In particular, the sharply peaked distribution that showed what was the volume that corresponded to.
So can you repeat
Oh.
the microphone for Zoom?
Can you repeat the question?
I think you want to, I don't know, there are two questions. You are asking about this peak? No.
The age.
So age distribution. Okay, so I didn't show any age distribution here. Okay.
Corresponds to
Okay. And so what was the question?
what volume?
So I think it's this is I didn't that's the 100 parsec sample. Yeah, it's all with Gaia data, and it shows the powerfulness of actually a spectroscopic survey, because now I think we are also entering the newer area with the era with the spectroscopic surveys, which give kinematics and chemistry.
The question? Do a quick one. In the white dwarf community, they're working on expanding the sample to larger distances. Any plans to move to like 25 parsecs?
For the white dwarf? No.
No, I mean for
Two plays. Not here.
Okay.
in the white dwarf community, they're working on expanding the sample to larger distances. You know, the 10 parsec sample that's complete and
No, first, I don't think the 10 parsec sample is complete.
no, I'm not saying.
And I think there are many efforts to go further away, in particular the Recons consortium, but not only to go further away, 25 parsec. The only difficulty is that you have to check more or less the object one by one. Not all of them, but some of them, and this is a very long.
Questions?
There's a question here.
Yes.
So the question is, do you have any idea what the upgrade catalog is? So what is this range?
Yeah, so we have to come in the splinter this afternoon to answer this question.